Hello and welcome to a new video on cryptography for everybody. In today's video, we will create mixed alphabets. For many classical ciphers, you need a mixed ciphertext alphabet. And the American Cryptogram Association, or ACA, defines 4 different keying schemes to derive mixed alphabets from an input or a source alphabet. And in this video, we will have a look at all these keying schemes and create our own mixed alphabets. I structured this video into 4 different parts. In the first part, we will have a look at the monoalphabetic substitution cipher. Clearly, you don't need mixed alphabets only for monoalphabetic substitution ciphers, but a monoalphabetic substitution cipher is a good example where you need a mixed alphabet, and this is why we included this in this video. After that, we will have a more detailed look at alphabets. Then we will have a look at the ACA keying schemes to derive mixed alphabets from a source alphabet. And finally, we will do it in CrypTool 2. We will use a new component that we created, or an updated component that we created, the alphabet permutator, to create our own mixed alphabets. What is a simple monoalphabetic substitution cipher? And when you're a subscriber of this channel, you probably already know this, but I think this is a good recapitulation what a monoalphabetic substitution cipher is. And the monoalphabetic substitution cipher encrypts using, and that's why we call it monoalphabetic, a single ciphertext alphabet. And here is an example. We have 2 alphabets. We have a plaintext alphabet. This is the alphabet used in our plaintext space. And then we have a ciphertext alphabet that we use for encryption. For example, our plaintext alphabet is just the standard Latin alphabet from A to Z. Then our ciphertext alphabet here is a shifted alphabet, like for instance in the Caesar cipher, that goes from D to C. And as you can see, it's shifted 3 times to the left. And how do we now encrypt using these 2 alphabets? We have a plaintext, for instance, hello world, and we have our ciphertext here. And when we want to encrypt an H, we go to our 2 alphabets that we have written on top of each other. We look in the ciphertext alphabet for the letter directly below the H. This is the K, and we write the K. Then we have a look for the E, which is encrypted by H. And now it's interesting because we have a double letter, 2 times the L. And here you can see also why we call this a monoalphabetic substitution cipher. Every time we have an L, we encrypt it with an O. So we have L encrypted by O, L encrypted by O. And again at the end, in world, we also have an L that is again encrypted by an O. Same as, for instance, with the O in the plaintext. O is always encrypted using the R. And as I have already said, each individual plaintext letter is encrypted using the same ciphertext letter. Now we could ask ourselves, what is the key space size of the monoalphabetic substitution cipher? And the monoalphabetic substitution's key space is the number, or are all permutated ciphertext alphabets we can generate. And this is 26 factorial. Why is this 26 factorial? For the first letter here, if we can freely choose, we have 26 different letters to put at this position. For instance, the D. If we decided to choose the D, we only have 25 letters for the remaining part of the alphabet. Now we choose the E. Then we have 24 different letters remaining to choose for the 3rd position and for the 4th and so on. And this can be described, or this can be computed using the factorial. So 26 factorial is the key space size, and this is about 2 to the power of 88 different keys, meaning different ciphertext alphabets. But despite this huge key space size, monoalphabetic substitution ciphers can be easily broken using frequency analysis. You probably also know this from my other videos. But it's fun by hand to break these ciphers also. And now it's the question how to generate alphabets and more easily memorize these. Let's have a look. First, we have a look at different types of alphabets. And as I have already said, we have a plaintext alphabet and a ciphertext alphabet. The plaintext alphabet is usually the Latin alphabet from A to Z. And the ciphertext alphabet can be, and here we have different choices. For instance, a permutated Latin alphabet like this here. This is just a random alphabet that we can use for encryption. Or it can be something completely different. And examples for something completely different are here. For instance, we have digits like 01, 04, 11, 25, 09, and so on. So we would encrypt A by 01, B by 04, C by 11, and so on. We could also have alchemical or astronomical symbols like these here. Then A is encrypted by this symbol, B by this, C by this, and so on. Or we could have a pigpen cipher. Then our ciphertext alphabet would look like this. We have these lined symbols here, like this left L shape, this U, this right L shape, and so on. You probably know the pigpen cipher, and this is a pigpen alphabet. We could use musical notes, or you could use any symbol that or any symbol set you can imagine. So you can be very creative in creating ciphertext alphabets, and in history people were also very creative in doing so. Now let's have a look at the ACA, at the American Cryptogram Association keying schemes. And the ACA keying schemes define how to permutate a Latin alphabet. And each scheme defines how the plaintext and the ciphertext alphabets are generated. In fact, you could just only permutate the ciphertext alphabet and always keep the Latin alphabet as plaintext alphabet, but the ACA allows to permutate both. But you will always find an equivalent substitution by having the Latin plaintext alphabet and then a corresponding ciphertext alphabet. And the ACA defines 4 different schemes that they call K1, K2, K3, and K4. And in each scheme, the alphabets may and should also be shifted. So they permutate the alphabet and then the resulting alphabet they shift. And in the following slides, we discuss each of the 4 schemes. Let's start with the first scheme, K1. The plaintext alphabet is keyed and the ciphertext alphabet is not. You will notice that in each scheme there's always a different sentence at this position here, which alphabet is keyed and which alphabet is not. And in this case we need a keyword. On all these keying schemes we need keywords, and for example we use the keyword secret. And as I said, the plaintext alphabet is keyed, so we change the plaintext alphabet, and the ciphertext alphabet is not. So what do we do here? At first we decide on an offset, for instance 3. So we go to position 0 here, position 1, position 2, and this is position 3. And in position 3 we write our keyword. And our keyword in this case is secret, but of course an alphabet cannot have 2 E's, so we have to remove all double letters, like the second E here. Then we have secret without the second E. And then we continue writing the remaining letters of the alphabet, of course omitting the letters that are part of the keyword. And when we come to the end here, we go to the beginning of the alphabet and we write the remaining letters of the alphabet. And now you can see how we encrypt with these 2 alphabets. For instance, when we want to encrypt the H here, we do exactly the same as in the previous slide. We search in our plaintext alphabet for the letter H. We look which letter is directly below this letter. This is the N, and we write the N. And for instance, the E here is encrypted by itself. So we write E here or E here. Then we have 2 times L. This is R. We have R here, and so on. This is how K1 or the keying scheme K1 works and how you can encrypt in the monoalphabetic substitution cipher with it. Now let's go to key scheme K2. And here the plaintext alphabet is not keyed, but the ciphertext alphabet is keyed. You could more or less say it's the opposite of the other keying scheme. Again, we have the keyword secret, and we apply the keyword now not on the plaintext alphabet, but on the ciphertext alphabet. Of course, we also choose an offset. I used in all examples the offset 3, but you are free to use another offset. Of course, the receiver of your secret message has to use the same offset. We write our word into the alphabet, into the ciphertext alphabet now. We remove the second E, of course. We write the remaining letters of the alphabet, and we have our ciphertext alphabet. And when we now encrypt using this alphabet, the H, for instance, we search for the H in the plaintext alphabet. We select here the T, we write the T. With the E, we do the same. Now we have LL here. L is encrypted by F. We write 2F and so on. And as you can see, this is a different ciphertext as on the previous slide. Now let's have a look at K3. And in K3, both alphabets are keyed using the same keyword. So we have, for instance, again, the keyword secret, but this time we write it 2 times into the alphabets. Of course, we have to choose 2 different offsets for the keyword in the alphabet, because if we choose the same offset, we create or we generate the same 2 alphabets for plaintext and ciphertext alphabet, and we would have no encryption at all. In this case, I've chosen the offset 0 here, so we write it at the beginning in the plaintext alphabet, write again our keyword and the remaining part of the alphabet. In the ciphertext alphabet, I again have chosen the offset 3, so 0, 1, 2, 3. We write our keyword here. Remember, removing the double letters or the occurrence of the same letter, the second occurrence of each letter or the third occurrence also. Then we have our keyword here. We write our remaining part of the alphabet as usual. And then when we want to encrypt, we do it as with both schemes before. With the monoalphabetic substitution cipher, you first search in the plaintext alphabet you've generated for the letter H, for instance. You get the letter D, write D, and so on and so forth. This is the K3 keying scheme of the ACA. Now let's have a look at the last keying scheme. And in this keying scheme, K4, both alphabets are keyed using different keywords. So we have a keyword, for instance, secret, and we have a keyword too that we have chosen, for instance, as keyword. Then in the plaintext alphabet, we again choose an offset. In this case, I've already again chosen 0. We have here secret at the beginning without the second E, the remaining part of the alphabet. And now in the ciphertext alphabet, we use the second keyword. We write it at an offset, for instance 3, keyword. We removed the double letters. Luckily for us, keyword itself has no double letters or occurrence of the same letter twice. Then we write the second alphabet after the keyword wrap around, and now we have our ciphertext alphabet. And encryption works as with all these schemes before with the monoalphabetic substitution cipher. We search for the plaintext letter in the plaintext alphabet, for instance the H, encrypted by A, the E here. Where do we have the E? Here's the E by an X, the double L here, the L is a G, and so on and so forth. So we encrypt using the monoalphabetic substitution cipher and 2 alphabets, a plaintext and a ciphertext alphabet. Yes, and these are all the 4 keying schemes of the ACA. Now that we know how the keying schemes of the ACA work, let's encrypt and decrypt with the monoalphabetic substitution cipher and different alphabets in CrypTool 2. I'm here now in the start center of CrypTool 2. I use the current nightly build 9294.1. This was created only 1 or 2 days ago. And this nightly build contains the alphabet permutator. And the alphabet permutator is a component that now implements all keying schemes of the ACA. So when you want to open it, you search in the template section of the Start Center for keyword, because we have a new template or a reworked template that's called substitution cipher using a keyword. And with double click, you open that template. And now we have here the template, and I think I probably in the way of the workspace, so I will remove me from the video now. So what do we have here? We have a text input for the plaintext. We have an example plaintext here. We have our source alphabet here. This is the alphabet that we use for deriving our plaintext and ciphertext alphabets. And as you can see, this is not only the standard Latin alphabet from A to Z. This is an alphabet with uppercase letters and lowercase letters. Why have we chosen this? We chose this because the text that we have here has also uppercase and lowercase letters. Then we need a password or a keyword, and this keyword here is secret, and we probably also need a second password or keyword, and we will add this later. And then we need a shift value for the alphabet. Now let's have a look at the alphabet permutator. When you click here on the right side, you get the settings of this component. And right now we have here all the ACA keying schemes from K1 to K4. In this template we have K2, but I think I will change this to K1. I will close this and I will add an additional keyword. So we have here keyword, and this is keyword 2. This here is keyword 1. And then we have an input in the alphabet permutator for keyword and keyword 2. I will put in keyword 1. And then we will have here keyword, a second keyword, as with our slides, as we used in the slides. And we have offsets here, or shift. These are shift values, not offset values. This is a shift value 2. And this is the first shift value, and I will change this to 0. Shift and offset value you can exchange. It's the same in the permutator. Now let's have a look at the settings again of the alphabet permutator. So we have the 4 keying schemes, and this here right now that this is a small bug that we need to fix in CrypTool 2. So usually this should be the complete size. So what can you do here? You can choose the keying scheme, for instance K1. Then you can choose, and this is not defined by the ACA, we added this, you can choose the order how the alphabet should be filled, or the remaining letters should be filled in the generated alphabets. You can use ascending, descending, or leave it as it is. I choose ascending. Then you can also define the keywords here in the settings, but I will use always the inputs here, the text inputs. And then you can do the same for the ciphertext alphabet. And depending on which keying scheme you choose, it changes the input and output, the input options or the generation options for the alphabets. Now let's have a look at K1. And now when we press play, as you can see here, the alphabet permutator generated a plaintext alphabet. Since we had chosen shift value of 0, you have secret at the beginning, that is our first keyword, and then the remaining alphabet. And with K1, the ciphertext alphabet is not changed. You have no keyword inside, but it is shifted by 3, as we have defined here. Now let's have a look at another keying scheme, K2. And every time the ciphertext should change since we change our plaintext and ciphertext alphabet. Now with K2, the first alphabet, the plaintext alphabet, remains. You can see here the standard Latin alphabet, uppercase and lowercase. And in the ciphertext alphabet now we have our keyword, and the alphabet is shifted by 3. Or you could say the keyword is at offset 3, but it's, as I said, the same more or less here. Then you can change to K3, and in K3 it should use the keyword 1 for both alphabets, so the same keyword. Let's have a look. We have plaintext alphabet, the word secret, the keyword secret at the beginning, and in the ciphertext alphabet we have the word secret at offset 3. And now finally with the K4 scheme we should have 2 different alphabets, same plaintext and ciphertext alphabet, one with the keyword secret and one with the keyword keyword. So we have again here keyword secret at the beginning and then the remaining part of the alphabet. And then we have keyword keyword at the third offset or shifted by 3, and then the remaining part of the alphabet. And as I said, you can also change, for instance, the ordering to descending or descending of the ciphertext alphabet. Let's have a look. Here you see first keyword at the third position and then the alphabet in the reversed order. Yeah, and this is how you can use the alphabet permutator. Yeah, and this is everything I wanted to show you in this short video. We have now all 4 ACA keying schemes implemented in CrypTool 2 in the alphabet permutator. I hope that you can use it for yourself. Maybe you can post below this video if it works well for you and what you did with it. Yeah, and as I said, this is everything I wanted to show you in this short video. thank you very much for watching. I hope you enjoyed it. If yes, please give a thumbs up. This really helps me to grow the channel and to make it more popular. So thank you very much for watching and see you in the next video.